Assalamualaikum and hi to all. This is chapter 3, gas turbine cycle, video part 3. In this video, I'm going to explain Brayton cycle analysis, the effect of pressure ratio, backwork ratio, and actual gas turbine cycle. Brayton cycle analysis. Brayton cycle analysis. So to go further on the Brayton cycle analysis, we should look into the PV and also TS diagram. So as you can see in the Brayton PV and TS diagram, we have two isentropic process, which is from process 1 to 2 and process 3 to 4. And for the TS diagram, we have a constant pressure heat addition process, which is from process 2 to 3 and process 4 to 1. So from the energy equation, which is given in this slide, we can expand this equation to be Q in minus Q out plus work in minus work out, and it is equal to H exit minus H inlet. And looking first at the heat transfer process, which is from process 2 to 3 and process 4 to 1, which is the constant pressure heat addition process. And we can calculate the Q in by using this equation, which is Q in equal to H3 minus H2 and Q out is equal to H4 minus H1. And from the cold air standard assumption, Q in is equal to Cp times in the bracket T3 minus T2 and Q out is equal to Cp times in the bracket T4 minus T1. And now we look into the isentropic process, which is from process 1 to 2 and process 3 to 4. So work in is equal to H2 minus H1 and work out is equal to H3 minus H4. So we also can use the pressure ratio from P2 divided by P1 and it is equal to PR2 divided by PR1 and it is equal to PR3 divided by PR4 and it's equal to P3 divided by P4. And as you can see in the PV diagram, state 2 and state 3 at the same is at the same pressure, and state 1 and state 4 also at the same pressure. And already mentioned earlier in this slide that in the process 2 to 3, it is a constant pressure heat addition, and whereas process 4 to 1 is the constant pressure heat rejection. So from the cold air standard assumption, we can calculate the work in by using this equation. Work in is equal to Cp times in the bracket T2 minus T1 and work out is equal to Cp times in the bracket T3 minus T4. And we also can we also can use the temperature and pressure ratio as shown in this slide. So T2 divided by T1 is equal to in the bracket P2 divided by P1 with the power of K minus 1 divided by K. Okay, so now we look into the gas law equation that state for this state all of the system we use the gas law equation, and PV is divided by T is constant. This is the gas law equation, and PA times VA divided by TA is equal to PB times VB divided by TB, and this is the gas equation, which is PV equal to MRT. And based on this process, we know that the thermal efficiency of the Brayton cycle is equal to work net divided by Q in. And we also can use this equation, which is 1 minus Q out divided by Q in. So the thermal efficiency from the cold air standard assumption is equal to 1 minus 1 divided by Rp with the power of K minus 1 divided by K. Rp here is the pressure ratio and K here is the specific heat ratio. And pressure ratio for the compressor is equal to P2 divided by P1 and pressure ratio of the turbine is equal to P3 divided by P4. However, for the ideal cycle of the Brayton, P2 and P3 is at the same pressure and P4 and P1 is also at the same pressure. So the pressure ratio is Rp is equal to P2 divided by P1 and it is equal to P3 divided by P4. So this is the analysis of the Brayton cycle. Please take note the PV and also TS diagram. And as your attendance, please state the energy balance equation of the Brayton cycle analysis. The effect of pressure ratio. the effect of pressure ratio on Brayton cycle efficiency. So this is the Brayton cycle efficiency, and this is the thermal efficiency of the Brayton cycle. And we all know that if we increase the pressure ratio of the Brayton cycle, we also can increase the thermal efficiency. However, there is a limit to this increment, because we should take note that the maximum temperature that the turbine blade can handle. So let's say we fix the maximum temperature, and however we increase the pressure ratio, as you can see in this TS diagram. So let's say we increase the uh, temperature and pressure at state 3 and state 2, so we can increase the work net out. However, we have a limit of the state 3, which is the maximum temperature that the blade can handle. And as you can see in the TS diagram, second test diagram at the bottom of your left hand side, so we have the maximum temperature, which is at the 1000 Kelvin, and the minimum temperature at 300 Kelvin. And this is, as you can see, we can still change the pressure ratio, which is from pressure ratio equal to 15, 8.2, and 2. However, whenever we plot the efficiency versus the pressure ratio, you know that the efficiency of the system varies, which is, if we increase the pressure ratio up to certain level, it will be at the maximum. However, if we increase more than that, it will turn out to be decreasing the efficiency of the system. Why? Because there is a compromise between the pressure ratio and also the efficiency with the work net output of the Brayton cycle. And the common design of the pressure ratio of the Brayton cycle is between the common design of the pressure ratio of Brayton cycle is equal to 11 to 16. Let's say if we increase the pressure ratio too high, and the work net output turn out to be low, because we need a large mass flow rate to maintain the same power output. Okay, large system may turn out to be not economical, so it does not increase, or it is not good for the thermal efficiency of the system. So this is the compressor of the Brayton cycle, and let's say we increase the pressure ratio, which is the RP. So whenever we increase the pressure ratio, we also will need a large mass flow rate into the system, and thus it will uh, need work into the compressor. Work in will be increased to the compressor, and the compressor size also need to be increased. So in that manner, it will be not economical to the system. Back work ratio. Back work ratio. So this is the diagram of the Brayton cycle, and what is the back work ratio? It is actually the how much the work by the turbine used to generate the compressor. This is the calculation, which is the back work ratio. It is equal to work by the compressor divided by work by the turbine, and it is also equal to work in divided by work out. Actual gas turbine cycle. Actual gas turbine cycle. So, as we all know, this before this we look into the ideal gas turbine cycle. So, however, in the actual gas cycle, there is the irreversibilities. So, there is irreversibility coming from the pressure difference from the heat addition and also heat rejection. There is a pressure difference between the heat constant pressure heat addition and constant pressure heat rejection process, and also in during the work, which is there is the actual work in of the compressor and actual work out of the turbine. So this is the actual diagram of the TS for the gas turbine cycle. As you can see, we have this process from 1 to 2S, which is the isentropic process, and process 3 to 4S, this is also is the isentropic process. However, in the actual process, we have the process from 1, it goes to 2A, which is the actual process, and goes to state 3, and there is a pressure difference here. As you can see, 2S and 3 is not at the same pressure, and goes to 4A, which is the actual position instead of 4s. So from this figure, from this TS diagram, we know that the process of 3 to 4a is not isentropic, and process 1 to 2a is also not isentropic, and there is a pressure losses there where the pressure at state 2 is not equal to the pressure at state 3. Same goes to the pressure at state 4. 4a is not equal to pressure at the state 1 due to the pressure losses. So actual behavior of the compressor and turbine from the isentropic efficiency of the compressor. This is the calculation of the compressor efficiency, which is equal to work from the isentropic process divided by work by the actual process, and it also equal to H2S minus H1 divided by H2A minus H1. H2S is the isentropic as the is the enthalpy of the isentropic process at the state 2S, and enthalpy at the state, and H2A is the enthalpy at state 2A. So based on the call as standard assumption, we can calculate the efficiency of the compressor by using the temperature, which is given as 2 T2S minus T1 divided by T2A minus T1. Whereas for the turbine, we know that the efficiency of the turbine is equal to actual work divided by actual of the isentropic process, and it is all equal to H3 minus H4A, which is the enthalpy at state 4A, divided by H3 minus H4S, which is the enthalpy at the isentropic process. And from the call as standard assumption, we can use the temperature to calculate the turbine efficiency. So effect on the efficiency of the BRAYTON, we can calculate based on this how to say the deviation between the actual and also the isentropic or ideal cycle. It affect the efficiency of the BRAYTON cycle, and you can calculate the BRAYTON cycle by using the same equation with the same work net divided by Q in, and it is equal to 1 minus Q out divided by Q in. This is the end of part 3 for chapter 3. Thank you, and hopefully you enjoy this video.